I've realized it's possible to fine-tune language models by updating only a tiny number of parameters. This can be done using LoRa methods, but it can also be done using representation fine-tuning, which allows you to tweak the activations rather than the model weights. I'm going to show you two examples today, one where I guardrail a model to resist responding with any financial advice, and the other where I cause a model to respond always in French, regardless of the question that it's being asked. You're going to find that this technique allows you to fine-tune quickly, and it should also enable you to create different behaviors that can be snapped together at inference time, something I'll talk about a bit more in a later video too. Here's what I'm going to be going through. To kick off, as I mentioned, I'll go through one guardrailing case where I prevent a model from giving financial advice, and the other one where it will always respond in French. Before going through the use cases though, I'm going to review the transformer architecture very briefly, because this will help us understand the difference between LoRa fine-tuning, which updates weights, and representation fine-tuning, which involves tweaking the activations at a specific layer and for a specific input token. So I'll show you each of those methods graphically, and then I'll move on to a full example of representation fine-tuning in a Jupyter notebook and do the same for LoRa, and we can see how they both perform and compare. Then I'll finish off with a few caveats on representation fine-tuning and also on LoRa fine-tuning. The libraries for representation fine-tuning are a lot less mature right now. They're not supported with VLLM or TGI just yet, but I think there are some nice features that will make them pretty interesting in the future. And the libraries are strong for LoRa, so you should be able to do much of what I'm showing today and deploy it at inference, in production applications. Just one other note as well, I'll comment a little bit on combining fine-tunes and when this works well. So let's get started and look back at the transformer architecture. I've made this really simple by looking at only a transformer with 2 layers. Typically, transformers like Llama 3 will have tens of layers within them. That's what makes it deep learning, because you have a large depth of layers. But it's much easier, of course, to look at just 2 layers. So here I'm looking at a transformer that's going to be processing 2 tokens, the words the and quick. And here I'm referring to the common phrase, the quick brown fox jumps over the lazy dog. So our goal is to input 2 tokens, the and quick, and we're trying to predict a token which should be brown. And here is our 2-layer transformer. And I want to step through what's happening at this input position for the as we go through this transformer. So first off, we have the token the, and there are going to be a specific number of tokens for a given language model. For example, there might be 32,000 tokens, or roughly that in Llama 2, or in Llama 4, the vocabulary is about, I think, over 120,000 tokens. So each of those tokens is going to have a lookup table. And in that lookup table, for every token, there's a vector. There's a vector in a high dimensional space, maybe in 1000 dimensions, that's going to represent that token. So when we start off with the token the, we're going to move through a lookup table and find the vector associated with the token the. Once we have that vector, which I've shown here in blue, that vector is going to be transformed in different ways. So it's going to be resized and redirected as it moves through the layers of the neural network. And these layers typically have exactly the same setup. So it's just a set of repeating layers. Here I've shown 2 of them. And in a conventional transformer, there are 2 important parts to each of these layers. There's the attention part, and there's the feed-forward or multi-layer perceptron MLP part. And these play different roles. The attention layer will typically gather information from all of the other token positions. Now, it will only gather information from the past positions. So since the word the is the first word, there's no information to gather from the left-hand side. But when we move to the word quick, the attention layers, the attention modules within each layer are going to be grabbing information from all the previous token positions, and they're going to use that information then to decide how to transform the vector for the word quick. Now, the multi-layer perceptrons, by contrast, don't necessarily take in direct information. They will rather take the vector and they're going to do some transformation on it. And the transformation is a trainable transformation that's controlled by a number of matrices. These, in the case of Llama 3, are called up, down, and gate. So these are 3 matrices of trainable parameters, that are going to move and reshape the vector as it goes through. So to recap, in each layer, you have the attention, which is going to take in information from other positions, at least those in the past. And then you have the MLP, or feed forward, which is just, you could call it a straightforward transformation of the information and of the vector into a different size and direction. And this process repeats then as we go up to layer 2, and we have an output vector. Now, the very same happens for the word quick. It will go to the lookup table where we'll find a specific vector. And note that the vectors for each of the tokens are also trainable. So in that lookup table, you have different vectors for each token, and those vectors are going to be trained throughout the training process. So we look up the vector for quick, we get it, and then that vector is going to be transformed, so moved in direction and magnitude as it goes all the way through, the layers. So again, in each layer, we're going to be having attention and a multi-layer perceptron module. The attention will take in past information and use that to transform the vector. And the multi-layer perceptron is going to just transform, but not taking in directly any information from previous input positions. And so you have this vector here for quick that's going to be transformed, and it's going to go all the way to the output. And once it gets to the output, it's going to go in reverse through the lookup table, and that vector will be converted back to a token, which is our final prediction. And I haven't shown that reversal here for the first position because we already know that and quick. So our goal is to calculate brown, and then we would take brown, put it down to the right-hand side, and we would propagate through a new layer, a new input position, and get to the next predicted token. Now, I'll say something that you might think is obvious, but is very important, which is that the weights that are used here, so the up matrix, the down matrix, the gate matrix, the Q matrix, the K matrix, the V matrix, and the O matrix, and the attention, these matrices of weights, they are trainable, so they're going to be updated in order to get the best match on output tokens based on a training data set. But these matrices are the exact same for every input position. So the transformer, when we talk about the transformer, we mean the weights. And the weights and the formula that are used for those, they're exactly the same at every single input position. What differs between the input position is that the attention will be taking in any given position, it will be taking in past information. So as you move to a longer and longer sequence, you're going to have more and more information that's going to be going in to each attention layer. And just notice how when we're in layer 2, we're going to be taking in information from layer 1. So the vector coming out of layer 1, position 1, is going to feed in and help guide the attention process in layer 2 of position 2. So what's happening at a much higher level when we think about transformers is we're converting words and we're transforming them into some kind of meaning. And that meaning is probably established as we get towards the middle of the network. Now, in this representation, I've only 2 layers. That's probably not enough to work well as a transformer. But in a deeper network, when we get to the middle, we're going to have some kind of meaning. For example, it might be German language. So there might be some aspect of a vector that indicates this is a German language. Or there might be some aspect of a vector that indicates this is sad. So what's being said is sad, just for example. So while we have these kind of brute force, or not so much brute force, but very mechanical descriptions at the entrance, we have these more abstract descriptions at the middle, and then we get back to rather mechanical representations at the output because we need to represent our tokens. And the reason why I'm telling you all of this is because when we think about fine-tuning, it would be nice, and when I say nice, I mean efficient. It would be efficient if rather than having to update all of the weights here in the model, so rather than having to update these matrices, these, it would be very nice if instead we could just tweak the meaning at some very targeted point, or even approximate point. But if we could switch the meaning so that it goes from, say, French to German, or German to English, or sad to happy, if we could just tweak that vector a little bit, that might be a lot more efficient than having to update or to train many, many more parameters. And so that's the big motivation for what I'm talking about today, is to figure out, well, can we find ways to just make a few little tweaks to parameters, and suspecting that it would make sense to tweak them where we have these abstract meanings. If we can do that, we can maybe save on efficiency, and run this whole fine-tuning a lot more quickly. So I've already shown this little red arrow that's just showing information flowing from an earlier position to the attention from a later position, and the same here from layer 1 to layer 2. And now I want to talk about weight fine-tuning, which is the fine-tuning I've talked about in all my other videos. So the idea with weight fine-tuning is you take all of the matrices in the transformer, so up, down, gate, and what you do is you are going to update those, so make some little delta changes to those matrices. And commonly we will do that to very many matrices, in fact, almost all. So we will make some updates to the up matrix, down, gate, the Q, K, V, O, and we will do that not just in one layer, but we'll typically do it in every layer, even like 32 layers or 70 layers or how many layers there are. So we'll make updates to pretty much all of the parameters within the weight matrices. And that's how weight fine-tuning works. And one of the ways that we make that a lot more efficient is instead of updating all the weights, we do what's called LoRa, which is low rank adaptation. So rather than training the base matrix, so if we have a matrix here, W, let's say W could be, for example, the K matrix in the first attention layer. If we have that matrix, which is 1000 by 1000, we'll say, no, we're not going to update that full matrix. We won't update those 1 million parameters. Instead, we're going to freeze this matrix and we're going to create some adapters. And we'll make these adapters a lot smaller. So maybe just of height 4, but of width 1000. And these adapters size this way, they can be multiplied by each other to give a matrix that's about 1 million parameters. So 1000 by 1000. But of course, with a height of only 4 each, that means we have only 4000 parameters for each of these two. So we'll be fine-tuning 8000 parameters instead of 1 million. And so the idea with LoRa is we forward pass through the frozen matrix, but when we update and make those delta changes, we only change these small adapters. And this very significantly reduces the memory that we need. So it reduces the VRAM we need for fine-tuning, because it means that we only need to keep the optimizer states for these reduced matrices instead of keeping them for the full matrix here. And it also means we only need to keep the gradients for these matrices here, the smaller ones, instead of keeping gradients to make updates to the whole matrix. So this is LoRa, and I talk about it a lot this is probably the slide that you see the most in my explanations throughout language models or even vision transformers as well. So again, if we're doing weight-based updates, we'll typically do LoRa in order to reduce the trainable parameters. But here's something new, and the something new is, how about we don't train the weight matrices? So how about we're not going to change up, down, gate, we're not going to change Q, K, V, O, and we're not going to change that for any of the layers. We're just going to leave them the same. Instead, what about if we focus on these vectors? What about if we focus on the vectors that are created, or rather updated by each layer? And these vectors, another word for the vectors is activations. The activations are the outputs of each of these modules or layers that we have. So what if we focus on updating these activations rather than focusing on the weights? At a very simple level, if we have an activation H, so let's just say we have a vector that starts off here, that's called X or H. It goes through one layer, and it's now an updated version of X or H. And what if we just add on a small delta here, which I've just called B? So instead of updating the weights, we're going to inject a little bit of meaning into the middle of this transformer. And the motivation here is we have some meaning that might be, say, German, and we're going to just tweak it with an added vector that's going to shift it towards being French. So here, B, this kind of brighter blue, that might be the French, German to French shift. So we're shifting the model's representation, which thinks it should be German, and now it's going to shift it towards being French. And this is our targeted idea of making a change to how the model is behaving. And in the same way that we updated the weights when we did a LoRa fine-tune or a full fine-tune, we can use gradient descent, and we can basically do an optimization problem with a new set of data so that we choose the value of this B. So we basically choose the strength and the direction of this update vector, so that we can minimize the overall loss on the new data set. And this is the idea of ReFT, or representation, or maybe you could also call it activation-based fine-tuning. And just in the same way that LoRa allows us to reduce the number of parameters we want to train, you can have low-ReFT. So you can do a low-rank representation of a low-rank representation fine-tuning. So you remember here, instead of training this full matrix with LoRa, where we update weights, we instead update these smaller matrices. Well, you can do the same thing. Instead of updating a full matrix here, that's 1000. What we can do is we can update a much smaller vector of size 4, and then we can have some kind of a rotation matrix that's going to project this or rotate this matrix, or not matrix, it's vector in this case. It's going to rotate it so that we can add it on top of the original frozen activation. Now, there are a few ways you can think of setting this optimization problem up, or setting up these adapters rather. I'll just go through a few of them. At a very simple level, to calculate the new activation, you could take the old one and you could add on some constant or some trainable parameter or trainable vector b, which is kind of what I showed back here. So h new equals h plus b. Now you do need to make sure that you're adding something of the same vector dimension, and that's why we have this rotation matrix here, or. So probably the simplest way that you could update the activations is just by adding in this trainable small vector b, and typically or the rotation would also be trainable as well. Now, what's actually being done behind the scenes in the ReFT notebooks we'll be showing today, or I'll be showing today, is a little more complex. I don't think the complexity is actually needed, but this is how it's currently being implemented. So h new is h, and instead of it simply being or times b, there's also a linear term here where there's a weight matrix multiplied by the existing activation h. So you can just think of this as kind of a constant or trainable parameters that are just numbers, versus here you have an affine or a linear function with a y-intercept. So it's kind of like y equals mx plus c, but here you've got wh plus b. So this is the update we're going to do. We're going to put in an update and we're going to target it. So we're going to target it at layer 15. We're going to take a look at Llama 3, the model that just came out. And rather than trying to update the representations after every layer, we're just going to focus on layer 15. And for one more twist, we're only going to apply this little addition at one position, at one token position. So you could think about, well, we'll put in this little boost here in direction and in size for the first position. You could additionally train a boost to go in here on the second position or the third. What we're going to do, and it's somewhat arbitrary, is we're going to apply it to the last of the prompt tokens. So if you have a prompt that says, why did chicken cross the road? Well, road is the position where we're going to put in this intervention here. So we can compare the performance of both LoRa and LoReFT. We'll try and set things up the exact same. So for LoReFT, we'll have layer 15 being targeted with this little vector change. We're going to focus on the last prompt token only, and we're going to use a rank of 4 for that fine tuning. So that just means when we go back here to how we set it up, the rank of the matrix or and w is going to be 4. And for the LoRa comparison, we're also just going to target layer 15. This is very different than what I normally do because I'll typically target all of the layers, and that's what you'll see in nearly every tutorial. But yeah, you'll be surprised with the results we get with just targeting one layer. And also, as is typically done with LoRa, we're going to apply this at all token positions. Just for clarity, all token positions. In principle, you could just target LoRa on a specific token. I think probably it would make sense to try that, but conventionally, and the way the libraries are written, it's applied to all of the token positions. Because transformers, as I described earlier, they make use of the exact same matrices for every single position. So it's kind of conventional to do the same thing at every position. But, you know, we like being unconventional. Just we don't like it enough to do the work that would be required for LoRa to be applied at specific token positions. Now, it is possible to choose which token positions to do LoReFT on. This is just because the library that ReFT is built on is called ReFT, LoRa PyReFT. It's built on PyVine, which happens to allow you to very specifically control the activations within a neural network, even down to the input position description. Okay, so we're ready to move to the notebooks. I've already described why this makes intuitive sense. We'll see if it works in practice. It makes intuitive sense because we're trying to intervene where there are abstract representations, and by tweaking an abstract representation, we think we can be a lot more efficient than having to just update the whole network. Now, if you want to read a little bit more on attention or multilayer perceptrons and how those individual matrices are used within a formula to process the direction of the vectors, you can check out these links, which will be in the presentation that I'll link below in the description. I'll now take a look into the two scripts, the LoRa-based script and the representation fine-tuning script. To get this going, I'm going to use a one-click template for RunPod. That's available in the public repo here, one-click LLMs. And if you choose the one for fine-tuning notebook, that will bring you directly to a page where you can start up a CUDA 12.1 template that has CUDA and PyTorch pre-installed. And what I did is select an A6000. I'm going to run on a fine-tuning on Llama 3, so that should be sufficient. And here you can see the template, which is the fine-tuning notebook. So with that, I'll click deploy and we'll be up and running. Once the notebook has started, I'll open up Jupyter Notebook, the web version, and I have uploaded here Tiny LoRa and also Trelis ReFT. These scripts are available in the Trelis Advanced Fine-Tuning repository. You can purchase lifetime access to that at trelis.com. That's trelis.com/advanced fine-tuning. In the case of ReFT, there are very many scripts that are already available. If you just go to PyReFT, type in PyReFT to GitHub, and you'll see a number of scripts for fine-tuning for representation. Let's start off with the LoRa fine-tuning just because it's more familiar and it'll be easier to explain what I'm doing, and then you'll see how the representation fine-tuning is a little bit different. The first step is to run the installation. There are two options within this script. One is a standard transformers installation, and the other is to do an installation with Unsloth. Unsloth is about twice as fast, but all of these fine-tunings are really fast, so you can choose either one. Once the installation is done, I'm going to select a model. The model I'll be running is MetaLlama 3. I'm using the version that's on News Research repository because this one here is not gated, so I don't need to log into Hugging Face. Next, I'm going to load the model. So I'm loading with the model ID. The device map is auto, which will automatically dispatch to the GPU. My torch D type is bfloat16, so I'm using BrainFloat16 because I have an Ampere architecture that supports it. This will allow for better precision. And flash attention is turned on for improved training speed. Next, I like to run some loading checks just to make sure that nothing overflowed onto the CPU. So it will print errors if something does overflow, which it hasn't. And next, I'm going to set up the tokenizer. So here you can see I have the beginning of sequence token and the end of sequence token for the Llama 3 model. And I have the end of sequence token now being redefined. So Llama 3, it has this end of sequence token, end of text, but actually the last token that's produced when there's a response is EOT_ID. So that's why I need to make the update here. Next, I'm going to set the pad token. Llama doesn't have a pad token, so what I'm going to do is define one. I'm going to define the pad token as pad, and then I'm going to add that to the tokenizer and set the pad token equal to that pad token. Now, because I've created a new token in the tokenizer, I need to resize the tokenizer embeddings. So after I've set that pad token in the model and checked that the model and tokenizer have the same pad token, I then need to resize the token embeddings. So what this means is that lookup table between each token and the vector, that needs to be sized to add one extra row for this new pad token. And you also have the option to pad to a multiple of 16. So this means it will add actually 16 rows. Sometimes the GPU operations, they like to have multiples of 16 in the calculations. And so it can be common to pad to 16 instead of just adding one row. Now there is a drawback to adding this extra token here. It means that now I've got some extra embedding vectors. And that means that when I run the fine tuning, with LoRa, it's going to save the full embeddings. And the embeddings are quite large for Llama 3 because Llama 3 has got a token vocabulary of about 120 or 30,000. Actually, there's about 2 gigabytes worth of embeddings that will be saved. So that means my LoRa adapters, which will also contain those saved embeddings, are going to be quite large. So it'd be nice if I didn't have to add that token and didn't have to resave the embeddings. There probably is a way to do that. What I'd recommend is maybe for the padding token to use what was the end of sequence token. So you could actually define the padding token as end of text. And once you have that set, you could then set the EOS token as EOT_ID. And that'll just mean you don't need to resize your embeddings because you're using a token that already exists. Okay, so moving on. I'm just printing the model here, and you can see the modules we talked about. So in each layer, there's the attention, and there's the multi-layer perceptron. And here you have the Q, K, V, O. There's also some parameters that are required for the rotary embeddings. Rotary embeddings, they provide positional information on the tokens. Then in the MLP layer, you have the gate up and down projections, as I described previously, and you also have the activation function within that multi-layer perceptron. The choice here is SILU. Sometimes you see GALU or RELU. These are different shapes for your activation function. Now we're going to set up LoRa. So here we're going to import the LoRa config and get PEFT model and set some of the parameters for the LoRa configuration. So first off, we have an adapter that is going to be of rank 4, and we'll use the same for representation fine-tuning. I'm using a LoRa alpha of 32. This is my recommendation for 7B models. For larger models, I recommend using larger LoRa alpha. Check out the video on LoRa fine-tuning if you want to have more guidance on using that and also rescaled LoRa. So I am using rescaled LoRa here, which will adapt the learning rate depending on the rank of the adapters I'm using. And notice how I'm only going to target layer 15, which is kind of in the middle. There are 32 layers, so right in the middle here, I'm going to apply a LoRa adapter, and I'm also only going to tackle the out projection. So I'm only going to tackle one of the matrices within layer 15. So if we go back here, you'll notice that there are many matrices we could choose to target with LoRa, but I'm only going to target the out projection here. So why am I picking the OPROJ, and what is that? Well, the OPROJ is an output projection, and it's part of the attention layer where you also have the Q, K, and V projection. And in simple terms, Q, K, and V are used together to pick out the relevant information from past tokens and then determine what that should imply for the current token position update. But after doing the QKV operations in Llama 3, there's an out projection, and that basically takes the outputs of the attention process and it basically does a simple linear layer on top of that. So you can think of the out projection as just a simple linear transformation of the attention that happens in each Llama layer. So I'm just going to focus on updating this with the LoRa adapter. And once that's applied through this command here for getting the PEFT model, we can check the number of trainable parameters. And because I'm only targeting one layer and I'm only targeting the O projection, the number of trainable parameters is really small. It's only 32,000, so 0.0004% of the total parameters. And I can even print out and see which modules are trainable. And you'll see the trainable ones are all layer 15, and it's LoRa B and LoRa A. Next, we'll set up some simple evaluation. I'm going to ask 2 questions. The first is, what are the first Fibonacci numbers? And the second is, do you think I should get a fixed or variable rate mortgage? The second question is trying to test whether we can get the model to say, no, I don't give any financial advice. So after running that, I just do some quick test evaluation on the base model, which is all very reasonable. It gives me some Fibonacci numbers and then gives me some advice on fixed versus variable mortgages. Next, I'm going to load the datasets for fine-tuning. You can, if you want, load a dataset from Hugging Face and then format it, but I'm just going to define 10 rows for each dataset here. I have a dataset here if you want to fine-tune a model to respond with emojis. That's based on work in the ReFT repository. Then I've created these other datasets. So this one here is to fine-tune the model to guardrail it against providing financial advice. And you'll see, for example, if I say, what should I invest in right now? It'll just respond, unfortunately, I'm unable to provide financial advice. So just these 10 examples, we can actually get some good guardrailing on a model and prevent it from giving that financial advice. Now I have two other data sets here. One is forced French examples. This one here will take in questions in a few different languages, like what is your name? And it will always respond in French. So it'll say, je m'appelle Jimmy. And I've also asked a few questions in a few other languages. Wo kann ich gutes Bier finden? So some German. Como está el tiempo? So Spanish. And then I even put in some Irish here. Conas is Federlum Dolgadi on Terfort. So all of these are going to be answered in French. Vous pouvez prendre un taxi. Okay. And we're just trying to force the model to respond in French, no matter what input we have. Now, if you wanted, you could also try to force French from English. This is probably a little more straightforward to fine-tune the model on, because it's just more consistent. We're saying, okay, if you get an English input, then give a French output, as opposed to saying if we have an input that's any of these four languages. So with that, I'm going to set the first example for this training. I've set it to force French examples. So we're going to force the model to respond in French. And I'm going to convert it to a pandas data frame and then format it into messages. So we'll have these this list of conversations between the user and the assistant. And with that, we're ready with our training data set. And we can pass that in, because it has a column of messages, directly to the SFT trainer. And the SFT trainer will automatically apply the chat template. So here's what this data set looks like. It's got 10 rows, and each row has got this user message and assistant message. Next, we're going to move on to training the model. And there are a few kind of unique things here. So we're going to use a batch size of 10, gradient accumulation of 1. And importantly, I'm going to use a very large number of epochs. And this is the opposite of what I recommend in a lot of my fine-tunings, where I have a large LoRa rank and a complex data set. Here, I'm going to have a very small LoRa rank, so a very small number of parameters being updated. And I'm actually going to overfit. So we're going to overfit on these parameters and get down to basically a zero loss on the training data set. And we're not going to worry about the validation data set. Now, the intuition here is that because we're fine-tuning in such a narrow number of parameters, the model should hopefully still generalize, because we're just inputting this very specific information. So hopefully we won't cause overfitting, even though we are going to overfit on this very narrow set of training parameters. One other little note here is that I'm only going to train on the responses. So that means I'm going to penalize the model based on the responses. I'm not going to penalize it based on predicting tokens within the question itself. So here we have the SFT trainer. All of the parameters are pretty common. You'll see I've commented out anything to do with the validation data set. And the learning rate I have put is probably on the high side. We've got a very small number of parameters, and that will lead to a high learning rate already because rescale LoRa is being applied. But even still, I've put the learning rate fairly high here. So gradient checkpointing is true. This will reduce memory a little bit. And with that, we're ready to run the training. Now you'll see here over 100 steps, the training loss falls and it eventually goes down to 0.002. So we have extremely low training loss. By the end, we've basically overfitted these examples. Next, we'll run the evaluation again. And you can see here, when I ask what are the first Fibonacci numbers, the answer is indeed in French. Les premiers nombres de Fibonacci sont de 0 à 1. And then, do you think I should get a fixed or variable rate mortgage? And the answer is, je vous conseille de prendre un taux fixe. So it's just straight off saying that you should get a fixed rate mortgage. So here you can see it's working fairly well. And note that I'm just fine-tuning to respond in French. This is not the fine-tuning with the financial guardrailing, which I'm going to show you in a second. In fact, when I run the one with guardrailing, let me see if I can just upload it here. So this is where we force it to respond in French. And I'm going to show you the example of the financial advice guardrailing on the representation fine-tuning. But I did run that also on LoRa. And what I want to show you now is quickly just combining those two adapters. So here, what I'm doing now is I'm going to reload the base model. I'm going to then load an adapter for no financial advice. and I'm going to then load an adapter that is for forced French. So when I combine these two adapters, I should get a model that's going to refuse to give financial advice, but is always going to answer in French. So I load the model here. I need to resize the embeddings after loading it because I added a new token to the vocab when I did that fine-tuning. And then I'm going to load, merge, and unload the first adapter, and then load, merge, and unload the second adapter here. And when that is done, I'll be able to inference using this combined model that has both of the adapters applied. So again, I'm going to ask these two questions about the first Fibonacci numbers and whether she got a fixed or variable mortgage. And you can see here, what are the first Fibonacci numbers? The answer in French is correct, and it's in French. And then when I asked, do you think I should get a fixed or variable rate mortgage? The answer is les conseils financiers. And this is kind of directionally refusing to respond, although the French is not exactly correct here. This doesn't fully make sense. So I would say that when you combine these two adapters, it's kind of getting the combined effect. My guess is that the issue is around the French. When you're trying to get a model to respond only in a language, I have found that you need to use more adapter ranks. So a rank of 4 is not great in order to just get a model to speak one language. I have found that using a rank of 8 or even 16, or potentially fine-tuning on more of the modules rather than just the out projection, is necessary to get good performance in language. By contrast, I think if you're doing simpler things like getting the model to respond with emojis, or even with the guardrailing example, you can get reasonably good performance using a fairly small LoRa rank. So this is my demonstration of LoRa, and you can see that you can get reasonable performance just by using a tiny number of trainable parameters. So let's take a look at the ReFT, the representation fine-tuning example. And as a recall, just remember that when we do representation fine-tuning, we're not going to update the weights of the matrices. Instead, we're going to add in this little adjusting vector to this vector here, which is an activation after the 15th layer. And interestingly, we're not going to do this at every input position. We're just going to do it at the last input position. So here it's shown at the first, but actually we're going to apply it at the last input position of the prompt. So let's take a look at how this works. And this script here is based on and heavily draws from the ReFT repository and the fine-tuning scripts there. So after the installation and loading the model and the tokenizer, again, I'm going to set the tokenizer end of sequence token, just as I've done here. And for the sample prompt, what have I got here? This is just an example of applying the chat template. So you can see here, I'm applying the chat template to this sample prompt to see what it looks like. And then I'm setting up this templating function. So ReFT in the examples, rather than using apply chat template, they use a more manual Python templating approach. And so I needed to set up this template, and to know the format, I just printed out what's been used in apply chat template. In the same way that we got a LoRa config, you get a ReFT config. Maybe technically it should be called a LoReFT config, but I guess it does have LoReFT intervention here. So it is indeed a low rank ReFT, a low rank representation fine-tune. You can see we're targeting layer 15. We're using a dimension of 4 for the adapter. The component we're targeting is the block output. This really just means we're targeting the attention after layer 15. And what else? We're feeding in for this intervention here. The embedding dimension is the hidden size. So this is basically just saying that what the dimensionality is of the activation, because we need that information when we're going to set up the adapters. Then, just like we do with LoRa, there's ReFT model, so get ReFT model instead of get PEFT model, and we input the ReFT config. And with that, we can print out the trainable parameters. And notice how here, because we're using a rank of 4, just because of the way it works out, the setup that's used for LoReFT, we end up with the same number of trainable parameters that we do in LoRa fine-tuning. Now, it's a bit of a coincidence that we get exactly the same number, but it makes sense that it's kind of roughly the same number because we're using the same rank. Remember also that just because we're only going to apply this in one token position, that doesn't save us any trainable parameters, because in LoRa, when we apply the LoRa to every token position, we're just talking about the same set of weights. The same weights are used at every position. So there's no saving in trainable parameters just by applying ReFT at one position. So here we have the very same examples. We'll be focused on the no-fin examples and the force French examples. And here we have data preparation. So notice how when this is being set up, we're going to use PyReFT make last position supervised data module. And this is where we're specifically saying that we'll only be targeting the last position of the prompt with this intervention. And when I say intervention, what I mean is adjustment of the activation vector at the output of layer 15 at the last position in the prompt. So with the data set up, we're ready to move on to the training args. We're going to train for 100 epochs, and we've got a learning rate here of 4e-3. So this is a really high learning rate. I possibly should have used the exact same learning rate in ReFT as in LoRa, just so I have a fair comparison. That's kind of a bit difficult because I'm using rescaled LoRa. Rescaled LoRa will adapt the learning rate according to the rank that I'm using. So maybe what I should have done is to turn off rescale LoRa and then set the same learning rate. My suspicion is that the lower learning rate being used here in the ReFT training is higher than what I used in LoRa. So I would expect that's why I'm getting faster convergence, which you'll see below. So when I do run training, the training loss drops really fast and it goes down to a really small value. So we're fitting that training data exactly. Now, when we run the examples, so we say, what are the first Fibonacci numbers? It says, I'm glad you asked. It's a series of numbers in which each number is the sum of the two preceding numbers. So this is a reasonable answer. But then when I ask, do you think I should get a fixed or variable rate mortgage? It says, providing financial advice is beyond my capabilities. So you can see here, the model, just with this tiny fine tune, is quite well able to guardrail against providing financial advice, while still answering questions that are not financial advice. Now, this is not to say you won't be able to get around the model. If I maybe cast some question that's financial in a non-financial way, then it might slip through. But still, it's providing definitely a primary layer of guardrailing. Now, there's one more technical thing I want to talk about, and that's around combining these ReFT interventions, which is analogous to combining LoRa adapters and merging them. And there's a quite nice technique that is possible with representation fine-tuning. In principle, it's also possible with LoRa, although it's not supported by libraries. And that is when you're fine-tuning, if you want to fine-tune for separate applications, you use orthogonal LoRa representations. So you might have one LoRa vector adjustment that's pointing in this direction for French, and then you'll have one that's at right angles, basically, although in very high dimensional space. So you'll have one at right angles that could be for doing something like responding in emojis. And the reason why it's nice to have them in right angles is because if they're at right angles, they won't interfere with each other. So when you add these adapters on top of each other, you're going to get kind of the sum of the effects. You won't get interference between them. And the way this is done here, there's actually a small bug in the code that I've put up on an issue, unless I'm just mistaken. I've put up the bug, so hopefully it'll be resolved soon and you'll be able to run through the script. But basically what this does is it allows us to take, say, a rank 8 adapter and use the first 4 of those ranks for fine-tuning for French and use the next 4 for fine-tuning for financial guardrailing. So I can just show you a little snippet here. Basically, we split up this rank of 8 into a subspace of 0 to 3 for no financial advice, and then we use 4 to 7 for a French subspace. And this allows us to set up orthogonal ReFT or orthogonal LoReFT fine-tunes that won't interfere, and so they can be snapped together at inference time without having interference. And in fact, when I showed you the example earlier of combining two LoRas, the reason why this answer may not be perfect is, one, I didn't use enough ranks for doing my French fine-tune, or two, it's possible I'm getting YouTube thinks I want you to give me a thumbs up. Or 2, it's possible there's just interference between the 2 LoRa adapters, and that's causing some degradation in the response. Just to add to that a tiny bit, I'll show you this here in the presentation. So what I'm talking about is the question of, can you combine fine-tunes, which you could do by combining LoRa adapters or combining representation fine-tunes. And the question I'm talking about is, will applying LoRa 1 or ReFT 1 plus ReFT 2 combine the effects of both? And at a really high level, the answer should be no, because transformers are non-linear. So you cannot just say, I'm going to do y if y is the transformer function. Y of a plus y of b is not going to be equal to y of a plus b. So if you've any nonlinear system, it's not going to be possible to just add 2 adapters and have the effect be equal to the combination of the 2 individually. However, there are 2 exceptions here that are particularly important. So the first exception is that, well, maybe I should start with the second exception. The second exception is that if you fine-tune in a way that they are orthogonal or perpendicular, so if you have an adapter where you're using 4 dimensions for fine-tune A and 4 for B, well, if they're orthogonal in high dimensional space, they're not going to interfere. And if you're only intervening at one specific position, so if you're only intervening, as I've shown, within one specific position in one specific layer, and they're orthogonal, that means you should be able to do it in a way that there isn't collision between the 2. However, there's a more general reason why you might be able to snap together LoRa adapters. And you may already know that it's quite common to merge models or to merge adapters, and it seems to work in practice despite these models being quite non-linear. And I suspect the reason why it works is because even if you're not perfectly orthogonal, so if you're not perfectly perpendicular with your 2 LoRa adapters, it's still really hard to have much collision when you're in high dimensional space. And the way to think about this is, if you think about 2 cars and they're forced to drive on a line, so that's one dimension, then the 2 cars are guaranteed to crash if they're driving in one dimension towards each other. Now, if they're in 2 dimensions, which is how cars normally drive, it's possible that they can crash. We have crashes all the time. Now, if you move to 3 dimensions like a plane, well, planes are much less likely to crash because there are 3 dimensions, so it's very hard for them to crash. And if you were to go up to 4, 5, 6, 7, 8, 9, the more dimensions you go to, and LoRa adapters are often in even 32 dimensions, it's pretty difficult to have 2 LoRa adapters that are going to have vectors, output vectors that are going to crash. And so there's this intuition that when you move to really high dimensional spaces, things end up being very close to orthogonal. They end up being close to right angles in most cases, just because the dimensionality of the space is so big and it becomes really difficult to crash. And so for this reason, it means you don't get interference as much as you think you would when you're combining models in a model merge or when you're combining LoRa adapters. Okay, so with all of that, I've shown you how to do LoRa fine-tuning with a small number of parameters. I've shown you how to do representation fine-tuning with a small number of parameters. I think both of these methods work quite well, particularly when there's a very specific meaning that you're trying to impose on top of the model's performance. If you're trying to impose more complex behaviors, like maybe very complicated function calling patterns with many different nestings or parallel calls, maybe then you still need to have a higher rank. Or maybe if you have something complex like a specific language and certain behaviors, you may also need to have a higher rank in order to achieve the granularity needed to get the performance there. Just a few notes before we finish on the limitations. So the representation fine-tuning, it's nice because you can target the activations rather than the parameters of the model. I'm actually not sure if there's really a difference between that. Possibly the representation fine-tuning and the LoRa fine-tuning end up being somewhat equivalent depending on how you set them up. I think there's more research needed to figure that out. Indeed, the representation that is being used, if you just check out here on GitHub, you can see that it seems the best performance or the most efficient performance from the representation fine-tuning is to do something like A times BH plus B. I mentioned earlier how maybe you could just do H plus B or maybe AH plus B as an adjustment of H, but it seems that these work poorly, and it looks like we're going to have more information on a paper that's due to come out soon. But my point here is that it's possible the way that you do these activation updates, it may end up being somewhat equivalent to how you do parameter updates, because this in some ways A BH plus B, it's kind of a feed forward layer, which means that adjusting the out projection may in some ways become somewhat equivalent. Now, just back to limitations here, representation fine-tuning, it's a fairly new library, so it doesn't have the same support as LoRa's. You can push models to Hugging Face Hub. You can train orthonormal parameter sets, but you cannot use VLLM or TGI just yet. You also cannot do continuous batching if you want to set up an inference endpoint. Right now, I believe that ReFT supports a single GPU only. And also, there's no flattening or merging of the trained parameters. So in the same way you can, well, not the same way, but in the way you can merge LoRa adapters on top of a base model, you cannot do that with representation fine-tuning. You would have to find some kind of a hack to put that representation within the main modules and apply it there. Meanwhile, for LoRa, you can push the Hugging Face Hub. It's supported by VLLM and also by TGI. You can even load multiple LoRa's on the fly with VLLM. This is something I want to show in a video coming up soon. You can do continuous batching, and there's the option to merge the adapters onto the base model to get a merged and new, fresh model. One of the caveats is that there isn't support right now, at least that I know of, to train orthonormal LoRa's. You probably can just train LoRa's anyway and snap them together and get reasonable performance in most cases. But maybe this would be a nice feature to have to ensure that there is less of a collision between the performance of different LoRa adapters. Just before I wrap up, a few quick comments. One question that might come to mind is, well, if we're training far fewer parameters, is the training a lot faster when we do this targeted LoRa or ReFT type fine-tuning? And the answer is, well, partially. So when you do fine-tuning with LoRa or with ReFT, you still need to forward pass through all of the parameters. So the saving when you use targeted LoRa or LoReFT is that your backward pass is going to be faster. And so you can reduce the time for your backward pass down to a really small amount, but your forward pass is still going to be the limiting factor in determining your overall training time. And since the number of parameters, even in what I'll call standard LoRa, is really small, you tend to spend a lot of time on the forward pass. And so there's not so much reduction in the total training time, just because you're going to further reduce the number of parameters from, say, 1% of the model down to 0.001% of the model. Another question you might have is, well, should I do any fine-tuning now with larger LoRa ranks, for example, 8, 16, or 32? And I would say, yes, it's still worth doing the training and trying it out with higher ranks. But now I think you should consider doing this very low rank training as well on a specific layer, usually a middle layer within the module, within the model. And the reason is, if your fine-tuning could have a representation that just needs to be tweaked in the middle of the model, you may end up with performance that is a bit more robust than doing a broader fine-tune on a larger number of parameters. Then again, you may find that the fine-tuning is not granular enough, and so it may actually do better if you use a larger rank. So really what I'm saying is that this is an extra tool to consider. It allows you to fine-tune a little bit more quickly in a more targeted way, and it can also have benefits in terms of having smaller LoRa adapters that need to be loaded at inference time, something I hope to get to in a video soon. That's it for this video. Do check out the GitHub PyReFT repository under Stanford NLP. And you can also find these scripts if you head over to trelis.com/advanced fine-tuning. Let me know the questions in the comments. Cheers.